Okay, looks like we have a good group here, and we can go ahead and begin. I want to thank everyone for joining today. Welcome to our EGI Fall webinar series, Discussions and Insight from EGI. Today's presentation is titled Energy and Decarbonization, Assessment of Low Carbon Technologies. Today we will be hearing from EGI Director and Professor of Chemical Engineering, Dr. Milind Deo. And at the end, we will have some time to answer questions that you may have. So with that, I am going to hand it off to Dr. Deo. And again, everyone, please feel free to put questions in the chat box below.
Okay, thank you, Jenny. Thank you all for joining our fall webinar, this last webinar of this year. I'm going to share some thoughts on energy transition and low carbon technologies. I'll share my screen. Okay, I will begin by showing you, most of you who are in the energy business know this, that energy is basically, people say it is the lifeblood of economy, but it also very critical to human well-being, as you see here. So there are basically three indicators of human well-being: health, education, and income, and these have been combined into what is considered the Human Development Index. And it's now plotted here, normalized, the high being 1, as a function of energy use per capita. And as you can see here, some of the more developed, wealthy countries are on the far end of this plot, whereas Africa, Asia, and some of the other lesser developed countries are on the left side of this plot. So energy not only allows for our availability of energy, allows for economic development, but also human development, which is highlighted here. But this is basically on a global scale, right? So lately, people have also started looking at parsing out this data on a more regional basis. And this is one of the later papers here back in 2023. And again, the same indices are mentioned here. This is life expectancy, education, and real income. They constitute the Human Development Index. And here you basically see the entire world. The lighter colors indicate higher human well-being, and the darker purple colors indicates lesser development, directly tied to the energy per capita use that you saw there. And now, as it parsed out, now this is now a blow up of the United States, and it's for the most part in light colors, but then you see some of the darker colors here. And then the state of Illinois is now further expanded into counties. Again, you see some lighter colors and some darker colors. And then the city of Chicago being expanded literally into neighborhoods. And then you see how the neighborhoods now are indicating the level of energy differences or disparity, even within our own communities. So what is playing out in the world is playing out literally in our communities. Even though this has been done for Chicago, it is true for most urban neighborhoods and urban areas here in the United States. So anyway, the point here is that there is significant energy disparity, and what we consider energy security, this is something that the world is looking for as we look at energy production and consumption as a whole. So this is happening in the context of energy transition, right? So there is this very big push for getting to net zero by 2050. Again, there are different corporations, countries, municipalities that have set some goals, more aggressive sometimes than 2050. And some of the key areas that are going to make this possible are renewables, carbon capture, hydrogen, and energy storage. There's a big momentum on hydrogen lately. So I'm going to touch on each of these different topics as we move through this presentation. As we look at this goal of getting to net zero by 2050, how are we doing? So here are, again, these are from EIA, some of the later plots. These are the latest available data, 2023. And you can see that the coal, this is production and this is consumption. And they kind of parallel each other. And you can see that the coal, both production and consumption, have dropped. This is only the US data, though, United States data. But you see that it is being replaced by natural gas, whose production has increased and so has its consumption. Crude oil, again, shows not a whole lot of change on these plots. So anyway, let's do a comparison. In the last 10 years, as we have moved aggressively towards energy transition, are we approaching net zero? So here is the 2030 energy mix, and here is the 2023 energy mix. Again, the striking point here is that the percentage of renewables, as you can see here, has stayed more or less constant from 2013 to 2023, in a decade in which there was significant emphasis on getting more out of renewables, while the petroleum percentage, which is natural gas and petroleum, actually increased from 62% to 69%, again, in the US, within the US. What about emissions related to energy? So the emissions related to energy, again, this is an EIA plot as well as projections. We did decrease from the 2005 base by significant amount as we transitioned from coal to natural gas. And now around 5,000 million metric tons or 5 billion metric tons of carbon dioxide per year. And these are the projections for high, low, and reference economic conditions. And at least by this particular measure, getting to net zero seems improbable, if not impossible. So even by our own measure and goals, we are not doing well. So again, as I'm trying to just put a couple of things here, one is this big picture of energy security, where the world is really hungry for more and more energy. And we are in a situation where we have kind of stagnated on the carbon picture. So what are the options that are available to us? Most of the choice of energy technologies, obviously from a sustainable point of view, obviously is cost driven, but now there is a big discussion and of course, analysis of carbon footprint. Sometimes we forget that there are other emissions associated with energy operations, and we need to look at those. For example, criteria pollutants, right? So we have to look at SOx and NOx and ozone and particulates and all of these. Sometimes we forget this. So that's one thing that, again, we have to keep in mind. Water is becoming more and more important. I did point out about energy security. And so what is the right metric in this? And in some ways, I guess the bottom line and the takeaway here is that all of these, I guess, in some sense, that we have to optimize it based on the situation and the location that is important. So again, this is one of the later plots from NREL on carbon footprints of different energy forms. This is kind of a busy plot, but you see that the electricity generation powered by renewables is on this side. If you consider storage options, it's in the middle, and then electricity generation powered by non-renewable resources is on the right. And this now has some data on carbon capture and sequestration projects for these fossil fuel resources. The important metric here to look at is the coal, which is almost a kind of a baseline number. It's about 1,000 grams of CO2 per kilowatt hour. And then everything else is scaled based on that, or at least you can look at everything else in relation to that. Oil around 800, natural gas about half of that, nuclear energy much less so. So this nuclear energy in this particular context is considered non-renewable, of course, because it does need a fuel that is non-renewable. And then some of the storage technologies are included, including hydrogen, which is somewhat newer. And I'm going to go into that in a lot more detail in the later part of the talk. And then all of the renewables are here, including geothermal energy, where EGI is doing quite a bit of research. So anyway, all of these are much lower, but in terms of the share of overall renewables as a fraction of the energy produced or consumed in the United States, the two biggest ones, of course, are solar, photovoltaic, and wind. And these are low, right? These are fairly lower as viewed in this particular context. But what about intermittency, right? So we have to look at so primary renewables are intermittent. So one metric that is used for looking at the viability of primary renewables like solar and wind is the levelized cost of electricity. And this has come down significantly. And I'm not going to go over that. That's a talk in and of itself. And these basically summarize different ratios of fixed and variable cost into a single cost metric and these have come down a lot. And in fact, now compared to the primary fossil fuel electricity generation. But what about intermittency? This adds a certain level of uncertainty as well as cost to operating these intermittent renewables. So there is a paper that one of my colleagues pointed out. The one idea is using this levelized full system cost of electricity, which condenses the cost of each technology into one number, but it's dependent on the market. And this is the reference there. And in this paper, there were two markets that were primarily looked at. One is Germany, and the other one is this Electricity Reliability Council of Texas, which is ERCOT. In Texas, because of the large generation of wind, particularly in Texas. So anyway, again, I'm not going to go into a lot of detail on how this optimization model runs, but basically the takeaway here is that LCOE, you see that these now, as I mentioned to you, are very are fairly low. In fact, comparing to natural gas, even in this context. But as you look at this other measure, which includes the cost of storage and intermittency, then for some markets like Germany, it is exceedingly high, and for Texas also, it's about 10 times higher than LCOE. And that obviously adds an additional carbon footprint to that needs to be considered. So they don't come without their own issues that again needs to be taken into account as we look at renewables. So one possibility, of course, is to use geothermal power as base power. And again, geothermal power on its own has a lot of different components to it. But currently it provides only 4 gigawatts of electrical capacity, which is, I think, less than 0.5% of all and all of it is from conventional geothermal. The hydrothermal geothermal plants like the geysers in California, most of the generation, in fact, is in 2 states, I think, California and Nevada. And then advances led by the FORGE that EGI manages, FORGE, Frontier Observatory for Research in Geothermal Energy, are driving new developments in enhanced geothermal systems where you're using the dry hot rock for producing electricity. And geothermal could potentially provide long-term storage as well. So these are 2 good advantages of geothermal, but currently it only does very, very small fraction of the electricity needed. And this is the FORGE site that is managed by EGI. And we have several PIs who work on this signature Department of Energy project in geothermal. 2 wells have been drilled. These are deviated, an injection well and horizontal well, both fractured and connected with water circulating between them. And lately, we have had some fantastic successes in this particular project, leading to a significant interest and fast-paced commercialization of EGS in the same location, but also elsewhere in the country. So some of the quick, again, this is a quick overview of some of the successes in FORGE, drilled highly deviated, larger diameter well, demonstrated some new drilling technologies, cut drilling times by 50%, which is a huge success. Stimulated these cased holes, again, in this dry hot rock for the very first time. Very successful circulation test in the last month, which almost bordered on commercial, and has a very excellent network for assessing induced seismicity to ensure that the project is managed safely. So basically, these advances paved the way for commercialization, and it is going at a much faster pace than even I think most people anticipated. With Fervo Energy, these are some of the press releases and announcements, has undertaken a large-scale EGS development in Utah, and also I think they have a sister site in Nevada, 400 megawatts, starting in 2020 to 2026 with full production by 2028. And then there is another company, Sage Geosystems. These are only 2 that I'm highlighting, but there are a number of them, about a dozen companies that are playing in this space right now, trying to make a big headway for using geothermal for base power and for other aspects for large-scale energy generation. But what about economics of EGS? Again, this is one of the later reports from Idaho National Lab and NREL. So here, again, I'm not going to go into a lot of detail. They looked at EGS only, or then combined with several other technologies, solar as well as natural gas. And this one shows a California location. LCOEs are reasonable, not that far off, but still have either marginally profitable or non-profitable project, according to this particular calculation, with a lot of the assumptions that went into this. And based on some of the newer results from Forge as well as other publicly available things, we are also taking on techno-economic analysis of these projects to see where they stand. So the options then available for to use energy as energy would be electricity, and then and for intermittent systems, storing it in terms for either batteries or there are several storage possibilities, including hydrogen. So hydrogen, which is an energy carrier, could be made using a primary source like natural gas or solar, and then stored and then used for other purposes. There are obviously thermal efficiencies associated with conversion of thermal power to electricity. So coal, as most people know, is about 30%. Natural gas, so simple power plants range in the 35% range. Some of the modern ones, 45%, and then the NGCC ones, natural gas combined cycle power plants, have started approaching about 60%. And hydrogen is in the same ballpark. There are very few hydrogen-only power plants in the world, and they're very small currently, but they are also approaching the 60% range. So most hydrogen currently is produced from steam methane reforming, which is about 10 million metric tons per year in the US. And here the thermal efficiencies are actually quite good, of the order of about 67%. So to make hydrogen from natural gas, we are looking at efficiencies of the order of about 67%. Most of this hydrogen is currently used in refineries or fertilizers. And there are quite a few studies looking at the carbon footprint of this and the cost of hydrogen. So this is without storage. So if you made hydrogen using natural gas and then took the CO2 and sequestered it, what type of life cycle GHG emissions you would have. So this shows this study by Wu et al. That appeared again recently shows life cycle GHG emissions of 4.5. This is definitely one option. So and there are some projects that are ongoing in Louisiana, particularly, I think, where CO2 is hydrogen is being produced from SMR, and being sick and CO2 being captured for either enhanced oil recovery or for cell and reservoir storage. And this report goes into the different types of tax credits that could be used then to drive down the cost of hydrogen. And it goes into a good bit of detail on where that cost appears and how that could be either lowered or optimized. But it falls within this less than $2 per kilogram of hydrogen, which is actually quite attractive. Anyway, so that's one option that is possible in terms of lower carbon use through the fossil fuel route. As I mentioned, on the energy storage, there are quite a few options that we have, and but again, we are at every stage as we transform from one energy to another energy form, we have to consider efficiencies because we are losing some part of that primary energy. And so for pumped hydro, it's considered reasonably high, and then it goes through these different technologies using hydrogen. The problem with pumped hydro, of course, is that you have it's very location dependent and very water intensive. So that's another thing that needs to be looked at. But this particular plot gives the power that could be drawn as well. So obviously, hydrogen, pumped hydro, and compressed air in the at least current form offer longer term grid scale storage compared to some of the other technologies. From a storage point of view, of course, there has been a lot of discussion about production of hydrogen and then storing it, and this gives you some idea of how much each of the storage options allow for. So here you have salt cavern storage is now currently being used, or at least being in a project form, and I'm going to talk about that. The other options are just listed here for reference, including this giant depleted gas field. But here, of course, there are risks of not getting all of the hydrogen back when it is stored in that particular form. So one contemplated life cycle for hydrogen, of course, is to make hydrogen using electrolysis, which is fed by renewables like solar or wind, store it in a salt cavern, and then as the prices allow, generate power using that hydrogen either in pure form or in combination with natural gas to get the electricity back. But as I mentioned, for each of these steps, there are efficiencies associated. So looking at the current available technologies, and these are improving almost on a year-by-year basis. But electrolyzer efficiency 65%, there are some storage compression losses, and hydrogen turbine efficiencies are of the order of 60% again. So the overall round trip efficiencies are in this 25% range, and sometimes could even be lower because of inefficiencies in transportation and so on. So there is an ongoing project here in Utah that uses this particular life cycle or this particular pathway. That is, I'll just give a quick overview of that with possible storage in depleted reservoirs. By the way, this particular cycle, there are a number of projects around the world that are currently ongoing. The one that I'm going to talk about is this Utah project, where in phase 1, 220 megawatts of electrolyzers will be brought in. These electrolyzers are already in place. 2 storage caverns, salt caverns, with brine evaporation ponds for excavating those caverns and associated equipment. It's only a couple of 100 miles from Salt Lake City. And in phase 2, this will add 330 megawatts of capacity. So again, a very large project. As you can see, almost in size, similar to what we looked at on the Fervo commercialization of EGS technology. So 2 parallel low carbon options that are looked at. So in this particular case, production is from electrolysis capable of generating 550. So both for phase 1 and phase 2, with 250 metric tons per day of hydrogen capacity, and currently is already installed and is being tested. The caverns themselves are solution mined. Each cavern is very, very large, 220 feet in diameter and 1,200 foot high, with 1.3 million meter cube of volume. It's relatively shallow so far as subsurface technologies go. And the bottom of the cavern is about 4,700 feet, 5,300 feet below ground. The capacity is each cavern is 5,500 metric tons with 150,000 megawatts generation. So when all 4 caverns or functioning, you will have 600,000 megawatt reserve. So it's a very large storage capacity. And this project is moving to a fuel mixture of 30% hydrogen, 70% natural gas by 2025. And there are very similar projects in Germany, Australia, China, and a few others that I have seen in various stages of development. But this is one of the first that will come online if it's on schedule for 2025. There is a group here, Dr. Powell and his students. They did looked at this life cycle and overall economics of this particular project for different electrolytic systems for again, I have a nomenclature table here. So this proton exchange membrane, different types of electrolytic system here with, so you can purchase electricity when it's at its lowest price, and then make the hydrogen, store the hydrogen, and then so they considered that in their optimization for 100 megawatt sizing of different cycles for proton electrolytic exchange membrane, for proton exchange membranes, for solid oxide, reversible electrolyzer fuel cells, and then alkaline electrolyzer, which is what is there in Delta, and then the combined cycle power plant, which is the technology that they will use. And then they looked at different metrics, including the cash flow for the projects, and found that with this arbitrage and ancillary services for hydrogen, these technologies could move into positive net cash flow, and then focused more on this electrolyzer, on the alkaline electrolyzer technology, which is being used in Delta, and basically showed the impact of the size of the plant, 100, 200, 300 megawatts, as you take you using that particular the arbitrage as well as ancillary services for hydrogen. So under certain conditions, this technology could be made profitable, and it is low carbon as well. But we have to consider the fact that the overall round trip efficiencies for hydrogen for this particular cycle are with the current set of technologies are still in the mid-20s. We could, of course, look at fossil fuels with carbon capture. So carbon capture either at the source or carbon dioxide removal using direct air capture. So those are possible technologies. The thermodynamic requirements for capturing carbon dioxide from these from fossil fuel exhaust are quite high. Right? These are minimum energy requirements for coal, which are approximately 13%. So as the concentration of carbon dioxide decreases, the minimum energy requirement increases. So you see that coal is in the 100 kilowatt hour per ton of CO2. Natural gas, which has about 5% in the exhaust, is about, anyway, it's higher. And then for carbon dioxide removal from air, it's it's much higher. These are minimum requirements, but the actual requirements based on some of the data that's available is even higher for coal, about 3 times that. Natural gas also higher, and then significantly higher for what is called DAC, or direct air capture, CDR. So this is, of course, a technology that is now being considered by at least a dozen or more companies at a large scale, and then I would say 3 or 4 dozen companies, maybe even more, at various stages of development. So it's 2,500 kilowatt hours per ton of CO2. So that's again with the current technologies that are being used. So CDR, the carbon dioxide removal, is energy intensive. The current processes use about 2,500 kilowatt hours of energy to capture 1 ton of CO2. So 1 ppm of CO2 in the atmosphere is about 7.8 gigatons of CO2 by mass, right? So reducing 1 ppm of CO2 will be equivalent to approximately 20,000 terawatt hours of energy. And the total world energy consumption currently is 30,000 terawatt hours. So 2/3 of all of world's energy that we use currently would be required to reduce the concentration of 1 ppm from the atmosphere. So this, again, we have to keep this in perspective as these companies, as we start going into large-scale operations for CDR. So even at extremely large operations, even at maybe 100 plants doing 1 million tons per year, from a practical standpoint, it's going to be difficult for us to see very many changes in atmospheric CO2 concentrations, at least based on these numbers that are currently. Again, one has to be realistic and be careful as we apply these technologies. So water needed for energy also needs to be considered. This is one of our studies that we did for the state for full life cycle analysis of how much water, again, normalized to gallons per megawatt hour for hydrogen. Again, there is a thought that because hydrogen by electrolysis uses water as a feedstock, it would consume more water than conventional technologies. It turns out that it is slightly higher than natural gas, but not significantly higher. And it's close to, when compared to natural gas with CCS, they are comparable in that range. And these technologies here that are listed here, coal, natural gas, are all with the current wet cooling technologies that are being used. There are some dry cooling newer technologies that are currently being considered and used, where the water use in these power plants will go down significantly, maybe to half the values that are shown here. If you go back and looked at the pumped hydro situation, hydroelectricity, as you see, because it stores such a large amount of water, this large amount of water loss is because of the large surfaces that are needed for storage or in hydroelectric power. So there is a nexus between energy and water. So there is water needed for energy production, which we saw on the last slide. But you can also use energy. Energy is needed for water purification. Again, the conventional thought is that, okay, so let's desalinate seawater. So we go with, say, that requires 0.86 kilowatt hours per cubic meter. in minimum, whereas actual energy in current technology is about 1.8 to 4 kilowatt hours per cubic meter. And thermal desalination requires higher amount of energy. And now there are some newer technologies that are being considered. Atmospheric water harvesting is still emerging, and no large-scale projects in this arena. But this requires generally higher water than desalination. But one of the things that again we can put in perspective is that the as we look at other types of energy requirements, the energy requirements for water purification are not that significant. So it does not add a big carbon burden for cleaning up water, which is also critical in some parts of the world. So again, the bottom line here is that you need water for energy, but the energy needed for water is comparatively less than other energy intensive processes. So at EGI then, okay, so one of the things that we do have to then consider is look at systems holistically. And one of the things we could, of course, do is decarbonization. And we have Professor Cody Powell and his group working with us on through their Intermountain Industrial Assessment Center for decarbonization and some of the hydrogen technologies that I showed some of their work. We have Professor Masood Parwania working on how to integrate renewables into the grid through their Wired Global Center for Grid Resilience. If carbon dioxide has to be considered, then we have Professor McPherson and his group looking at carbon storage particularly. I showed some of the work from Utah Forge. We have Professor Moore and Professor McLennan leading that effort for EGI. So we have basically world expertise, I think, in geothermal, and we have created a consortium to advance those technologies further. We continue to work in conventional oil and gas, both onshore and offshore, considering that these resources still have to be used in a responsible way and to provide adequate energy for all of the world, and expanding into areas of hydrogen as well as critical minerals. So I am proud to work with all the our partner faculty and research staff here at Energy and Geoscience Institute. So some closing thoughts here. Energy is precious, so we should be very careful in how we use it, and we should minimize wastage. So energy is precious, don't waste it, is one of the things that we should say. Carbon dioxide is expensive and difficult to deal with, so don't make it if it's possible not to make it. And in addition to cost, when we look at these technologies, our optimization really should consider, of course, other types of emissions. Energy efficiency is sometimes lost in the debate, I think. Carbon footprint, of course, as we look at these low carbon technologies. Water usage is becoming more and more important. And then, of course, we shouldn't forget about energy security as well. So this particular NASA image is of flares. This is an older image, but still shows this large amount of gas being flared in Eagle Ford. So this is kind of a signature example of what we shouldn't be doing with energy, which is wasting it. Anyway, I think that's my last slide, and close with that. I'm happy to take questions.
Milind, it looks like we have some questions in the chat box below. Are you able to see those?
Okay, there are a couple of questions from my old friend here, Santosh. LFCOE does not take into account externalization cost of CO2 emissions. Also, with fossil gas, the cost of methane is unaccounted for. Does LFCOE discount the cost of emissions? I don't think it does that. I think it's a straight calculation with respect to the financial considerations that would increase the the levelized cost. So yeah, if those are considered, that those I think costs would be higher. But right now there aren't, I think, established techniques for mitigating at least methane emissions out of fossils. What pathways are being looked at for improving the round trip efficiency of hydrogen storage? I think there is a good bit of research being done on the electrolysis. I think that's one thing that where that particular pathway is to increase the efficiencies there. And also, I think the materials as well as turbine operations for improving efficiencies there. So that those parts of the cycle are considered for improvement. Why combine fossil gas with hydrogen? Yeah, that's actually a good question. Again, if hydrogen becomes an end use for several applications, as I said, there's a good bit of momentum, not only for hydrogen production, but also for hydrogen end use. And as we would need more hydrogen that only can be delivered through I think natural gas, where established technology of SMR. So we would produce hydrogen and then increase its use for other purposes as we ramp up the electrolysis or the green hydrogen production. And a lot of that, I think, is being considered and done in these different hydrogen hubs that are being looked at. Okay. Yeah, there are the follow-up on that. I think there are a number of large options available for new battery. Yeah, that's true. I think new battery technologies are also coming on, and that the grid level battery storage, at least in my reading, I'm not a battery expert by any means, is still quite expensive and is not very practical. So the next question: any thoughts for developing geothermal wells in Kenya, for example, where private power producing companies are currently suppressing geothermal development since they have access to country's electricity grid and use hydropower mostly? I think, yeah, especially unlocking this particular technology that Forge has enabled would make it possible, I think, world over to implement EGS in the right geologies. Again, I'm not very familiar with the Kenyan situation, but I don't see why that couldn't be considered, assuming that these projects that have started here in Utah are successful. Next question from William Sero, who is one of our alums here. Should we worry about water usage in all these technologies for H2 production? Based on at least our analysis so far, obviously in some regional context, water scarcity might come into play, but in comparison to other energy production technologies, water from electrolysis doesn't add uh, that, that much additional burden. So I wouldn't think that water would become a constraining factor for hydrogen production. A question from our friend here, Michael Vandenberg from Utah Geological Survey. Any thoughts on the future of energy research and development in light of an event that happened on Tuesday? I would rather not comment on that. But I think there is the industry has taken this on, right? So I think uh, uh, the momentum that has been generated toward whatever we are seeing, both with respect to decarbonization and balancing this low carbon usage with energy security, because with all the discussion, right? So my first couple of slides basically showed that with all the discussion of energy transition, US is still producing record amount of oil, right? I mean, that is still happening. And I think it will continue for the next several years, next decade or so at least. So I don't see, at least, okay, so this is going on a limb here, but fundamental changes in how we are working in this energy business. Any other thoughts or questions? It's an exciting time, I think. There are obviously challenges, but a lot of possibilities. And those of us who are in this business would have I think, an exciting time looking at solving some of these critical problems. So any view on global energy landscape? On the global energy side, as I said, the first couple of slides somewhat summarized what I was saying. China might be an exception, but I think most of the developing world still relies on conventional energy. And I think that is probably going to continue in the foreseeable future. And that's why I think it will be challenging to, even if net zero can be achieved in some local context, maybe in large local context, let's say even European context, um, um, I think it will be very difficult to get to globally net zero by 2050.
Dr. Dave, this is Simon John from Dow. Can I ask you a question?
Okay, let me quickly address a couple of other questions here. Dr. Brown, thank you for your question. Rich Brown, who was the Dean of Engineering for the last, I think, 20 years or so, has also joined the webinar. Thank you. Slide makes the case that we will never get close to net zero emissions. How do we change the societal expectations to a more realistic view? I don't know the answer to that. I think continuing our education, I think, is the key uh, key to that. Continuing to talk about these issues in a more straightforward way. Scandinavia also, yeah, I haven't looked at that specific case. This is again a question from Santosh. Nearly non-fossil energy use. Yeah, as I said, it's quite possible to do this. I mean, Iceland and New Zealand and places where geothermal is available in plenty. With small populations, I think this obviously can be pulled off, but going to be challenging globally, especially as we look at Africa and some areas of Asia, including India. Okay, Simon, please go ahead.
Oh, yes. Thank you very much for the presentation. I have to say, I enjoyed two classes you taught us, the kinetics and green engineering. I consider it as a privilege to come to your seminars again.
Thank you.
So
Thank you.
I have a
Appreciate it.
question about some of the green hydrogen projects you demonstrated in your presentation. Is any of them supported by the Green Wells program from APA-E?
I know that the Delta project did have either loans or grants directly that were from Department of Energy. So it was initially benefited significantly from DOE investments. I don't know exactly in what form. It could be ARPA-E.
Okay.
But at this time, of course, the project is the project is owned by Chevron, at least the subsurface component of it, and working with Mitsubishi on electrolyzers and the turbines. So I think now it moves into more private funding in that context. Again, I'm not exactly sure how the financing has worked out for that project.
Oh, okay. So from an EGI standpoint of view, are you focusing more on the green hydrogen or blue hydrogen side? Or what are you in your radar? Which one is?
So we have an ongoing project on natural hydrogen that is headed by Dr. Setayama, looking at possibilities of producing hydrogen at various concentrations naturally through, again, that's ongoing research, looking at storage in salt caverns and then other geologically diverse locations. And then the optimization work, as I was mentioning, with Professor Powell and his group. So there are several components of hydrogen that we are looking at.
So particularly on the hydrogen storage, right?
Yeah.
Okay.
Hydrogen storage because of our strength in subsurface science.
Thank you.
Okay. Maybe one last question here. Again, one of our former colleagues here, Blake Billings. In your last slide, you mentioned that a big point is being careful how we use our energy as it's precious. That would lend itself to increasing energy efficiency. How do we promote energy as a decarbonization foundation? Yeah, I really think that must be followed, I think, again, through almost continuous education and outreach, because it literally creates this win-win-win proposition, right? You have lower energy, lower emissions, as well as a lower carbon footprint. So I think, need all of us as a community to go out there and preach that, because it's something that everybody can and should believe in. This energy efficiency.
Okay, do we want to wrap up, Milind?
I think so. Yeah,
Okay.
thank you for all the questions. And again, thanks for all of you who joined the webinar, and we continue to look forward to interacting with you.
Yeah, thank you everyone for joining us today. We will be having a spring webinar series, but we don't have a schedule yet. So go on to our website, egi.utah.edu, to subscribe to our newsletter, and that way you'll get updates on when we'll have those dates. Okay, thank you everyone. Oh, and we will make this presentation. It was recorded and it will be made available. It will go up on our YouTube channel and will be on our website. Thank you, everyone.
Thank you.